prove that the relation R on the set of integers Z defined by A comma B, that's the ordered pair, belonging to the relation R if and only if A plus B is even is an equivalence relation on Z. Okay, let us begin. Now here it's given that R is on Z. Now this simply means that R is going to be a subset of the Cartesian product of the set of integers with itself. And we have a definition for R that's given here, that R is a set of ordered pairs A comma B such that A plus B is even. A plus B is even where A and B are integers. Right. We have to show that the given relation is an equivalence relation. Now, any relation R is said to be an equivalence relation if it follows from the fact that the given relation R is reflexive, it is symmetric, and it is transitive. So let's quickly go through the definition of each of them. Now, R is a relation on the set A, then our relation R is going to be reflexive if and only if the ordered pair A comma A belongs to the relation R for all values of A belonging to the set A. Then number 2, R is going to be symmetric if we have the ordered pair A comma B belonging to the relation R would imply that B comma A also belongs to the relation R for all A comma B belonging to the set A. And then finally, R is going to be transitive if we have two ordered pairs A comma B and B comma C belonging to the relation R would imply that A comma C also belongs to that relation R for all A, B and C picked up from the set A. So what we'll do for our relation R, we're going to check if it is reflexive, symmetric and transitive. If it is all of them, then we can say that R is an equivalence relation on Z. Okay, let's start by checking out for reflexivity. For this, we're going to consider an element. So let A be an arbitrary element. So let A be an arbitrary element in Z such that, now here A we're considering an arbitrary, so it could be an odd number or it can be an even number. Now when we say that A comma A belongs to the relation R, then this would imply, since our relation gives us A plus B is even, so all we have done is replace this B with A. That should give us A plus A is even. Now is that a true statement? Yes, that's definitely a true statement. So if we consider A to be an even number, so let's say A is 2. So adding 2 to 2, that all gives us 4, which is also an even number. We can check this out with odd numbers as well. So if we consider the odd number 3 and add 3 to it, then that's going to give us 6, which becomes an even number. So that means addition of 2 even number gives us an even number. Addition of 2 odd number also gives us an even number. So that means this statement A plus A is even, it is a true statement. So we can say that R is reflexive relation. So this is going to be a reflexive relation. Okay, fine. So one is done. Now let's check number 2. R is symmetric or not. Now to check for symmetry, what we'll do here, we are going to consider two elements A and B. So let A and B be two elements. These are two arbitrary elements that belong to the set of integer C. Now such that we're considering, if we consider A comma B, the ordered pair A comma B belonging to the relation R, then according to the definition, it means that A plus B is even. Okay, now whatever be the value of A and B, whenever the moment we say that the ordered pair A comma B belongs to the relation R, it simply means that A plus B is even. Now we know that addition is commutative. So A plus B can be also expressed as B plus A, and it still means the same thing. That means B plus A is also going to stay as even. But the moment we write B plus A, now we can say that the ordered pair B comma A belongs to the relation R as well. Fine. So if this is the case, then we can say that our relation R is symmetric as well. So this is a symmetric relation. Okay. So that takes care of the second one. Now finally, we're going to check if R is transitive or not. So for this, what we'll do, we're going to consider three elements A, B and C. So let those three elements be A, B and C. These are three arbitrary elements that are picked up from the set of integers. Now if we have A comma B belonging to the relation R, now if we have this ordered pair belonging to the relation R and we have another ordered pair B comma C which also belongs to the relation R, our goal will be to show that A comma C also belongs to the relation R. In other words, we have to show that A plus C is an even number. Fine. Okay, so let's try to verify if it is true or not. Now, a comma b belonging to R simply is telling us that a plus b is even. This is an even number. And b comma c belonging to R is telling us that b plus c is even as well. Now, if we say that a plus b is even, can we not say that a plus b is a multiple of 2? In other words, we can say that a plus b is simply equals to 2 times m. And b plus c is also even, so we can say that b plus c, that is also an even multiple of 2, so we can say 2 times n. Well, we are going to consider m and n to be some arbitrary integers z. We don't have to worry about its value. Now let's add both of the two equations. So we get a plus 2b added to c. This is going to be equals to 2 times m added to 2 times n. So we're going to transpose 2b to the right hand side such that we get a plus c equals to 2 times m added to 2 times n minus 2 times b, such that we have a plus c equals to, we're going to factor out 2 from each of the 3 terms on the right hand side. We get 2 multiplied to m plus n minus b. Now m and n, these are integers, and we have considered b to be integers as well. So m plus n minus b, this is going to be some integer. We don't have to worry about it. So let's do one thing. Let's replace it with some integer b, where we have considered m plus n minus b to be equals to p, where p is some integers. Okay, now a plus c equals to 2p. Now what is this telling us? This is simply telling us that a plus c is divisible by 2, or in other words we can say a plus c is even. A plus c is even, so that is what was our goal, to show that a plus c is even. So a plus c is even simply means that the ordered pair a comma c also belongs to the relation R. So here we can say, so our relation R is transitive as well. So therefore we have successfully showed that our given relation R is reflexive, it is symmetric as well as transitive. Hence we can say that relation R is an equivalence relation. This is an equivalence. It is an equivalence relation. It is an equivalence relation, and it is going to be defined on the set of integers z. Hence proved.